Division 3, concrete. Division 3 of CSI format is concrete. Every time we start a new subject, particularly a material that is used primarily for structure, we will look at the value of the material in terms of structure versus finished material. We will look at the core component of the material product, and we'll look at the pros and cons and ways that we could actually take care of its negative concerns. All right. So concrete is primarily used as a structural material. Up to 1980s, it was used as a finished material, and we recognize that it has several flaws as a finished material, so using it as a finished material has slowed down substantially. Concrete is extremely plastic. You can form it, and it has been more and more a recommended material when we have complex forms and shapes. It has high strength. It is fantastic in compression, not very good in tension. In order to provide for its weakness in terms of tension, we use rebars, we use reinforcement, we use metals to reinforce it. It is a fantastic material in terms of fire protection. There are concerns about weight, and we can find ways to reduce its weight, but it has major issues with respect to weight. We will review the mixture, we will review curing, we will review the admixture, and some of the short-term versus long-term issues. So let us start with the components of this material. Sometimes it's referred to as cement, and that's not a correct term. So concrete is made out of aggregates, using coarse gravel, limestone, granite, finer materials such as sand and other additives. Cement, Portland cement, fly ash, and slag cement. There are a few other variables as well. These have to do with the specific use of concrete, water, and it has to do with hydration of the cement and the chemical reaction with cement. Chemical admixtures are used to slow down the process, speed the hydration, and some minor other uses. Reinforcement is used to take care of its weakness. Steel is fantastic in terms of tension, therefore it is used for reinforcement. Concrete is fantastic in compression. Direct vertical force at its center is ideal. Then we have precast concrete and poured in place. Precast is fantastic in terms of getting very precise form and shape. You can control the temperature, the amount of water, proportions, and the curing process. However, limitations are transportations and the fitting. Then we have the process of poured in place. It is far less precise but far more flexible in terms of the outcome of the form. Sometimes it's cheaper, certainly we're not concerned with the transportation as much. Then we have post-tension and pre-tension. As we add rebars, we can have the rebars go into post-tension and then add force on it, or place it in a pre-tension and then transit so that it counteracts as the loads are applied. We'll see the diagram shortly. All right. The curing, 27 to 28 days. However, it's very important to understand some of the basics. Cement requires a moist, controlled environment to gain strength and harden fully. The cement paste hardens over time, initially setting and becoming rigid, and later on gradually in the following weeks it gains its full strength. Generally, within the first day or two, 24 hours to 48 hours, it gains enough strength so you can walk on top of it. After 7 days, it gains about 50% of its strength, and it can actually gain some ability to take more load. But it's really after 4 weeks, at 4 weeks typically gains about 90% of its strength, that you can actually apply the load. It's very important to understand the conversion of calcium hydroxide in the concrete into calcium carbonate from absorption of CO2 over several decades, which then gives it the strength of concrete. So once you understand that, it's important to process, and you also have to remember, as this chemical reaction takes place, it can impact the rebars, the reinforcement, and corrode them, and we have to watch for that as well. Now, concrete is great in terms of strength, so let's give us unit of measurement. Concrete strength is measured in pounds per square inch, PSI. So when we're not concerned heavily on the strength of the concrete, and we're doing just slab on the grade residential construction, 2,000 PSI is good. Once we get into parking garages, concrete slab that is structural, we get into 5,000 PSI. As we get into high rises, far more concerned with load, we get into 10,000 PSI. Very, very unusual for bridges and very complex projects. We go up to 36 PSI. All right, so that gives you a sense of strength of the concrete. Now, as we said, concrete is good in compression, bad in tension. Let's understand that in a horizontal member. As we apply load on a horizontal member, the top of that member goes into compression, and we have a little bit of concern with that compression configuration. The bottom tears apart and pulls on either side, and concrete is horrible with tension, and that's when we need to apply reinforcement towards the bottom of the concrete beam, concrete slabs, any horizontal member. In a vertical composition, vertical structural member, because concrete is great in terms of vertical compression forces, compression strength, it is best to apply the load to the center of the column, providing vertical support at its center. We call it column supporting axial load. When we shift the load to the side, we call it eccentric load. Column supporting eccentric loads are not appropriate for columns. For that reason, most concrete columns are in cross-section, square, any shape that is equal distance to its center, and we apply the load axial at its center. All right, so as we said, reinforcement, we apply it to the bottom because steel is good in tension and concrete is good in compression. All right, so steel, metal rebars are used for tension. And we talked about precast versus poured in place. Post-tension versus pre-tension. Post-tension versus pre-tension. All right? So precasting concrete, right? So once the load is applied, it's the bottom that goes into tension. So we can put it in pre-tension. So once the load is applied, pre-stressing the concrete, once the load is applied, it goes to that shape condition that we're looking for once we apply the load to it. So, pre-stress concrete, this shows the diagram for it, all right? So essentially, whether it's post-tension or pre-tension. Now, when you look at a cross-section, this is a diagrammatic cross-section of a horizontal slab going into beams. Here you'll see that the reinforcement runs in two directions. In that direction, and you can see with these circles which suggest the rebars going 90 degrees to these members. Now, from there to there, we've got 100% tensile strength. the overall length of the slab is from the center of this beam to the center of that beam. We can refer to it as L. So going into the L dimension, we know the ends of that horizontal member, be it beam or slab, goes into tension. So here you see, comma 2, comma 3, L, we go into tension on the top as well as tension on the bottom, okay? So this diagram suggests the distribution of steel. So 50% of mid-span steel, we go into this, tension at the top. That gives you a sense of diagram. This little table, I copied it from the site. The reason I'm showing it to you is because it says the length, the L, has to do with the width of the slab. So length and width are both important. Spacing of the bars, how far apart these are, has to do with that L and W. And then edge clearance is important. Bar size is important. Bar size, when we say 5, number 5 means 5/8 of an inch. Overlap percentage is important. Slab thickness is important. All of these issues are interrelated. In addition, adding complexity of vertical forces or diagonal forces that come at the columns and beams at the ends. All of those play a major role. For that reason, other than residential simple span, simple slab, architects do not complete this process. Architects could use these tables only for preliminary dimensioning. Engineers will go in detail, calculate all of those required distances and sizes. So this rule of thumb table essentially says number 3, number 4, number of rebars. So we say 4 is 4/8 of an inch, 5, 5/8 of an inch, okay? Diameter. Number 3, 3/8 of an inch. Number 5, 5/8 of an inch. And it takes care of that amount of square inch in area. So that gives you a sense of sizing of the rebars. Now this table I like to make reference to is rebar rules for distance to the edge of the concrete. So the general rule that I like you to remember is if you're using an 8-inch slab, 3 inch to the bottom of it. If you're using 6-inch slab, 1.5 inch. But you have to think about these issues, which has to do with minimum/maximum size of the rebars, conditions in terms of exposure to the earth, exposure to movement, exposure to other structures. All of that plays into the rule. Connection of the slabs plays a major role, whether you're connecting the slab vertically to a structural column or wall. This is a diagram which is somewhat outdated, suggesting CMU wall connected to the slab. Very similar to our school, but this system is outdated. But I just wanted to show you, so when you see these reinforcements sitting on the ground, they get connected as such. Again, remember, every time we're connecting any member to another member, we're experiencing tensile strength. So all of these gadgets that you see here will provide for that tensile stress, which needs tensile strength. So these gadgets embedded into concrete slab or column, extremely critical. So these suggest whether you do precast, post-tension, and whether you have diagonal members. Look at the diagonal members, rebars coming out, vertical members, and obviously if we increase the surface of the transition of the load, it is preferred. So the upside down column is obviously very clear here. The two vertical and diagonal column takes care of the tensile strength, vertical compression strength. So although architecturally it creates an awkward space and removes some usable space, in terms of structure, this crisscrossing is very much needed for some types of structure. I wanted to show you this image because it shows you what happens that during the process of curing, you have corrosion of the